Hello, guys. Welcome to another episode of CUDA Education. So we are now on Clean Slate 2.2. Um, and basically, what we are doing now is we are investigating the AAPL renderer file. So in the 2.1, we investigated AAPL simple, and that was a shader file, right? So a shader file is GPU instructions. It's a .metal file. Now we're going to investigate AAPLRenderer.m, as you could see here, here, and here. Okay, and that is basically just regular source code, if you will, but it's setting up things for our application to run. Now, of course, we are still in our just regular, you know, partial bistro scene where we have some assets over here, and some things are being rendered. Obviously, it's not being rendered to its fullest extent. There's still work to be done, but this is an improvement over our previous situation where we just had an orange triangle, right? A weird looking orange triangle, but we are moving towards our, full bistro scene. Now, if you're new to the discussion, if you're new to the series, to the channel, Clean Slate is basically starting a fresh Xcode project, right? Fresh and clean, brand new. Xcode is the GUI for all things related to Apple development, things of that nature. So we start a fresh project, and then we basically make improvements to get to basically the most advanced application in the Apple Metal sample library, which is the modern renderer application. So the modern renderer application is a full-on bistro scene with lights and fog and a skyline and skyscrapers and shadows and tiles and texture and trees and all that stuff, right? So we're trying to go from a blank clean slate project all the way up to the most advanced application in the Apple Metal sample library, right? And it's called Modern Renderer, two words put together, Modern Renderer. That's the name of the application. So we're trying to go from absolutely nothing to that state, and we're trying to learn as much as possible as we make the steps towards towards that ultimate goal. Now, I'm not going to pretend that I'm I'm not an Apple Metal veteran or a computer graphics veteran that's been doing this stuff for 100 years. So as you learn, I learn. As I learn, you learn, right? And that's just the way it is. So we are now in the AAPLRenderer.mm file. Again, we started with a triangle. Well, first we started with a blank screen, then a triangle, and now we're at this, right? So we're just now trying to figure out what is going on. So let us get to AAPLRenderer.mm. So there's a header file and a main file, file. I don't even know how to, but anyway, a file. And what this is implementation of the renderer class, which performs metal setup and per frame rendering. Okay, so before we had a triangle, and now we have this. So if we look at the includes, well, I'm sorry, not includes, the imports. If we look at the imports, we see that we have, before we just had APL renderer, APL camera, APL shader types. In the new situation, with our new drawings and stuff, we still have renderer, camera, and shader types, but now we have APL mesh, APL asset, APL texture manager, and APL mesh types. Okay, notice that these are all .h files. Okay, so .h are sort of header files. You can include them in one place or many places, what have you, and they just help out with giving you capabilities and stuff like that. Okay, so let us see what's going on with that. We have that. we also have, right, so, basically mesh asset texture manager mesh types, right? A lot more stuff going on, a lot more things involved. We also have this sphere in Frustum thing right here. Tests a bounding sphere against all 6 frustum planes. If the sphere is entirely behind any plane, it's invisible and we skip drawing it. This is frustum culling, a critical optimization that avoids sending geometry to the GPU that would be clipped away anyway. All right, so guys, I've extensively, just even in my Vulkan episodes and stuff, we've extensively discussed frustum, right? So the frustum is basically what is viewable by the camera that we're by the camera and by extension, what we see on our screen, right? So there's a far plane, there's a near plane, there's a left, right, upper, lower plane, all of that stuff, right? It all adds up to 6 planes. And what we want to make sure is that, what we see, we only process, we only do the geometry, the calculation, the work of what we see inside of our frustum, inside of our camera's line of sight, right? If it's outside our camera's line of sight, we're not going to waste time, energy, effort, and our battery power. If we're running our machine on a battery, we're not going to waste it, calculating stuff that ultimately we won't see. So basically, I could guess that, all of this that we're seeing right here is part of it. It passed the frustum culling test, right? It passes the test, so it draws. But like, for example, this building would extend out further to the right, right? But the part of the building that's not viewable by the frustum or viewable by the camera is not drawn for obvious reasons, right? We're not into wasting energy. So that is what this whole frustum culling is. So we have a before and after instance variables, okay? So yeah, well let's so returns true if the sphere is at least partially inside the frustum, right? So they sort of break up these tests into spheres, which I don't want to go out on a limb and say it's it's what I kind of seen previously in Vulkan and stuff, but basically these tests are done in spheres, right? So it's like a big sphere, and you kind of try and see, okay, I have this sphere here. Is what I'm considering to render, is that inside of the sphere or not, or is the asset inside of the sphere or not? So maybe going back on what I previously said, but maybe just part of this building is inside of the sphere. So it might have, because it does say here, test a bounding sphere against all 6. If the sphere is entirely behind any plates, it's invisible and we skip drawing it. This, right, so if we have a sphere, and the sphere is basically trying to say, okay, these are the boundaries of the things inside of the sphere. These are the outer boundaries of the things inside of the sphere. If the entire sphere is not, right, if the entire sphere doesn't hit up against the any of the 6 frustum planes, basically the box that signifies what the camera can see. If the sphere doesn't hit any of the 6 planes or 6 sides of the box that the camera can see, then we just discard. We don't render what's inside of that sphere. That's what's called tests a bounding sphere. So we're testing the bounding sphere to see, this sphere encapsulates a bunch of things, and we got to test the sphere. If the sphere fails, where it's not inside of the box of what we can see, then we know we could discard or neglect rendering everything inside of that sphere because it failed the test, right? So that's basically what this is. Returns true if the sphere is at least partially inside the frustum, right? So so maybe with this thing, maybe the rest of the building is rendered based on how the granularity of the sphere. But basically we try and break apart what we do render and not render based on these spheres. And of course, things are then decided based on what happens with the spheres, right? So returns true if the sphere is at least partially inside the frustum. So sphere and frustum, we have a bunch of parameters. We have the camera and we have the sphere, right? And we're basically saying if the sphere is inside, or if it's not inside the frustum, then we return false. Otherwise, we return true. Now, I guess I'll just pause here and just actually play around with this. So right now, we have this for thing here, and inside of the for thing we have this test, and if this test fails, then we return true, right? And all of that stuff. But let's not dive too much into the logic. What I want to show is that so basically we have, if the test pass, if the sphere is in the frustum, we return true, right? If it's not in the frustum, we return false, right? That's what we want to take away from this logic right here. So right now we have this as returning true because it's inside of the frustum, right? It's inside of the box that's viewable by the camera. But if I were to change this to false, right? If I were to change this to false and then rerun, right, we would see that everything disappears, right? Because we're basically saying no matter what happens, everything, all the spheres fail, everything fails, right? And our object disappears, right? So obviously that is not what we really want. So we're gonna replace it back to true, and then we're gonna see that we have our object here, okay? So that's all that is. Nothing too special, nothing too crazy, right? So that's for the sphere and frustum helper function right here. All right, so before and after instance variables. So now we have instance variables. We have simple pipeline state, vertex buffer, color buffer, and camera. That was before. That's what we had before. And then after, we have mesh, pipeline state, texture manager, mesh, and camera. So we still have camera, and we still have an MTL render pipeline state, but notice that it's a different variable, mesh pipeline state. And now instead of vertex and color, we have texture manager and mesh. So these guys get booted out of camp, and now we have these guys right here. And that's basically what, let's see if we could find it inside of the file. So we have that guy. Let's see. I believe this might have been in the header file then, right? Is that what? No. Okay, so the hard-coded triangle buffers are gone, replaced by the texture manager and load mesh, right? So I'm going to assume then that we are in aha. See, I was looking for MTL buffer, but my bad. Okay, so we have our we have our mesh pipeline state here, and then we have the texture manager here, the mesh here, and the camera here. Okay. The hard-coded triangle buffers are gone, replaced by the texture manager and loaded mesh. Okay. So things are getting a little bit more involved, as we could see right here. Let us continue. Before and after load metal with view. So before loaded vertex simple shader, fragment simple shader, created a pipeline with no vertex descriptor. So load with metal, load metal with view. So after we now, because we got rid of, notice that we got rid of vertex buffer and color buffer here. We're not really working with that anymore. So after we have AAPL texture manager, right, with creates a AAPL texture manager with 1.5 gigabytes of heap for textures. 1.5 gigabyte heap for textures. So I'm trying to get to the because somewhere in here is the 1.5 gigabytes. So create an APL texture manager with 1.5 gigabyte heap for textures. So it's this guy right here. Notice that we have a heap size, Command Q heap size, texture size, max texture size, use sparse, what have you. Load vertex mesh shader. All right. Loads vertex mesh shader and fragment shader, right? From the default library. Creates a vertex descriptor. This is new and important. Okay. Create the vertex descriptor for mesh data. Each vertex attribute lives in a separate buffer, not interleaved. Okay. So that's all of this guy right here. So we have this guy right here. Okay. So this guy right here. The vertex descriptor tells metal position data lives in one buffer. Normal data lives in a separate buffer, each with 12 megabytes of stride. Now, layout for positions buffer stride equals size of float 3 equals 12 bytes. So each with 12 megabytes stride. So layout for positions, 12 megabyte stride. Layout for normals, 12 megabyte stride. This non-interleaved layout matches how AAPL Mesh stores vertex data, each attribute in its own MTL buffer. So I was hoping to see something with buffer right here, but okay. Okay, so that's that for... This is all within load with metal view. So we have load with metal view. We have our texture manager here, a 1.5 gigabyte heap for textures. We have a vertex, MTL vertex descriptor, creates a vertex descriptor for mesh data. Mesh data, each vertex attribute lives in a separate buffer, not interleaved. So we have this guy. We have right, we have the vertex descriptor for position for normal, and then we know that it's a stride. We know there's a stride for positions of 12 and a stride for normals of 12. Okay. All right, let's go to load assets. So before we created a hard-coded 3 vertex triangle buffer, and after we have mesh data, APL mesh data, bistro.astc.bin, and then mesh, init with mesh, all of this stuff here. So let's go to that. Okay, so we now have our APL mesh data, okay? And what we want to do, this triggers the entire asset pipeline. Mesh with file name, maps, the 309 megabyte binary, reads header, deserializes with NS keyed on archiver, okay? So APL mesh data, load the bistro scene from the compressed binary asset. So we have APL mesh data, mesh with file name, bistro at ASTC bin, and then NS assert mesh data failed to load if we fail to load the bistro thing. Okay. So that's mesh with file name, okay? And then we have init with mesh. Decompresses all vertex index material data into GPU buffers, loads textures into the heap. So this is some heavy stuff right here. Init with, so we have our mesh variable here, and we have our mesh data variable here. Okay. So the device is the device, texture manager is our texture manager. I guess this is where the 1.5 gigabyte heap comes into play. And if we don't, if we fail to create mesh from asset data. So, So this is how this gets passed into this. Init with mesh, right? So mesh data, right? So this and this get passed in together, right? So fail to create mesh from asset data. Okay, so what we get is fail to create mesh from asset data, right? So if it doesn't load, but that's how these two communicate with each other. Decompresses all vertex index material data into GPU buffers, loads textures into the heap. Before and after, draw in MTK view. So then we're getting into, let's see, where is draw in MTK view, okay? So draw in MTK view. So draw an MTK view. Draw a single triangle with draw primitives, vertex start, vertex count 3. So this was before, and then after we have a bunch of stuff that we added in. Let's just go through the key differences. Key differences, so it's all this guy right here, right? The key differences from the triangle version: draw index primitives. Instead of draw primitives, uses an index buffer so vertices can be shared between triangles, far more memory efficient. So this is basically like if I have one triangle here and then I have another triangle here, I could reuse this indexed vertice. I don't have to rename this vertices. I could just use this reuse this index vertices because it helped to draw this triangle and it helped to draw this triangle, right? So this one right here is sort of reused, which means it's more memory efficient. You're not filling in more space with, because you're just using that same indexed thing. So uses an index buffer so vertices can be shared between triangles, far more memory efficient. MTL type UI, MTL index type unsigned int 32. Each index in a 32-bit unsigned int pointing into the vertex buffers, right? Per submesh draw calls. Each submesh is a group of triangles sharing a material. Per submesh draw calls. Each submesh is a group of triangles sharing a material. We issue one draw call per visible submesh. And then Frustum culling. So Frustum culling is before each draw call, we check if the submesh's bounding sphere is visible to the camera. Invisible submeshes are skipped entirely. So let's look at update camera, get render pass descriptor, create command buffer and render encoder. All right, yeah, this is our command queue for the GPU. And then we create our render encoder, set pipeline state and depth stencil state. So set render pipeline, mesh pipeline, depth stencils, depth stencil state, set camera params, all of this stuff here. Bind mesh. Underscore mesh, vertices underscore mesh normals, right? Okay, so here's where we skip submeshes outside the camera frustum. So notice that we're looping on I. So submesh is submesh I, which is this variable here, and then if it's outside, we just continue. Otherwise, we put it as part of the encoder. So notice that we have our submesh here. And obviously we'll have to get into this in granular detail at a later date, but for now we just want to get a quick understanding of the big picture. So if it's not part of the frustum, we skip over it, but if it is part of the frustum, then we add it to the encoder. And this we just loop through all of the submeshes, okay? And that's that for this. And then we end encoding. Right, so you see issue, each submesh is a group of triangles sharing a material. We issue one draw call per visible submesh, okay? So that's this guy right here. Frustum culling. Before each draw call, we check if the submesh's bounding sphere is visible to the camera. Invisible submeshes are skipped entirely. So that's what this guy is right here. We skip it entirely if it's not part of the thing. And that's it for this episode, guys. That's it for this episode. This is CUDA Education. Let us just go through quickly. Okay, let's just go through quickly what we discussed in this episode. So, first thing, we included mesh, asset, texture manager, and mesh types, okay? We included that. And then we have a sphere in frustum thing. So let's just go to, just go all the way to the top, and we'll just review one more time, right? So we included a bunch of stuff here, right? We have our sphere in frustum to test whether something is part of the sphere. And we saw that if we put everything to false, then our object here disappears, right? We saw that. That's what the frustum culling is, a critical optimization that avoids sending geometry to GPU that would be clipped away anyway, right? So we saw that. Then we went to our instance variables, right? Which is down here. So we have our mesh pipeline state. Notice that we got rid of vertex and color, and we put in mesh pipeline state, texture manager, mesh, and camera. Okay, so we have mesh pipeline state, texture manager, mesh, and camera, right? The hard-coded triangle buffers are gone, replaced by the texture manager and loaded mesh. Okay. Then we get to load metal with view. So we get to load metal with view. Before, loaded simple, vertex simple shader, fragment simple shader, created a pipeline with no vertex descriptor, right? But now we have an AAPL texture manager with 1.5 gigabyte of heap for textures, right? So this texture manager thing right here, and then we load vertex mesh shader and fragment mesh shader from the default library, right? And importantly, we create a vertex descriptor. This is new and important, right? Creates a vertex descriptor for mesh data. Each vertex attribute lives in a separate buffer, not interleaved, right? The vertex descriptor tells metal position data lives in one buffer, normal data lives in a separate buffer. Each with 12 megabytes of stride, right? So we know that create the vertex descriptor for mesh data. Each vertex attribute lives in a separate buffer, not interleaved. So we have our vertex descriptor here. And we have a bunch of stuff that we have to add to it. But more importantly, we know that for the positions it's 12 megabytes of stride, and for the normals it's 12 megabytes of stride. Okay? And for load assets, we have before created a hard-coded 3 vertex triangle buffer. And then after we have APL mesh data. Mesh with file name. This triggers the entire asset pipeline. Mesh with file name. The 309 binary reads header deserialized with NSKey on archiver, right? So this guy right here. So this gets collapsed into mesh data. This mesh data then goes into mesh, and we associate this with this through here. Init with mesh here, the device is the GPU, texture manager, all of that stuff, right? And that's what this init with the decompresses all vertex index material data into GPU buffers, loads textures into the heap, right? So we have our draw in MTK view. Draw a single triangle with draw primitives, vertex shader after. We have all of this right here. Key differences. Draw indexed primitives. Instead of draw primitives, use an index buffer so vertices can be shared between triangles, right? We have a per submesh draw calls, right? Each submesh is a group of triangles sharing a material. We issue one draw call per visible submesh, right? So that's what this guy is all right here. The draw call is here. All of this right here, Frustum culling. Before each draw call, we check if the submesh's bounding sphere is visible to the camera. Visible submeshes are skipped entirely, right? So that's this guy right here. We skip it if it's not part of the thing. So yes, guys, I definitely would agree this episode is a rough one, but we got through a lot of meaningful stuff. Obviously, we can't go in granular detail with everything, but at least we have a better idea of what's going on. I'm sure in later episodes, I will circle back to this stuff and get into more detail. And that's why I have the clean slate numbering system. So this is going to be, I believe, clean slate 2.2, and obviously focused on the AAPL renderer, file. And we'll develop it at a later date, the details, but we just want a high level understanding of what's happening in order for us to create this guy right here, right? I believe if I were to just do that, right, so if I skip this encoding right here, we basically neglect our mesh that we were supposed to have, right? So if I put this encoding back, we get back our object. Okay.